Test-driven development is a software development process that relies on the repetition of a very short development cycle. First, the developer writes an automated test case that defines a desired improvement or new function, then produces the minimum amount of code to pass the test, and finally refactors the new code to acceptable standards. Kent Beck, who is credited with having developed or rediscovered the technique, stated in 2003 that TDD encourages simple designs and inspires confidence. Test-driven development is related to the test-first programming concept of extreme programming, begun in 1999, but more recently has created more general interest in its own right. Programmers also apply the concept to improving and debugging legacy code developed with older techniques. Test-driven development cycle. The following sequence is based on the book Test-Driven Development by example. 1. Add a test. In test-driven development, each new feature begins with writing a test. To write a test, the developer must clearly understand the feature's specification and requirements. The developer can accomplish this through use cases and user stories to cover the requirements and exception conditions, and can write the test in whatever testing framework is appropriate to the software environment. It could be a modified version of an existing test. This is a differentiating feature of test-driven development versus writing unit tests after the code is written. It makes the developer focus on the requirements before writing the code, a subtle but important difference. 2. Run all tests and see if the new one fails. This validates that the test harness is working correctly, that the new test does not mistakenly pass without requiring any new code, and that the required feature does not already exist. This step also tests the test itself. In the negative, it rules out the possibility that the new test always passes, and therefore is worthless. The new test should also fail for the expected reason. This step increases the developer's confidence that the unit test is testing the correct constraint, and passes only in intended cases. 3. Write some code. The next step is to write some code that causes the test to pass. The new code written at this stage is not perfect and may, for example, pass the test in an inelegant way. That is acceptable because it will be improved and honed in step 5. At this point, the only purpose of the written code is to pass the test. No further functionality should be predicted nor allowed for at any stage. 4. Run tests. If all test cases now pass, the programmer can be confident that the new code meets the test requirements, and does not break or degrade any existing features. If they do not, the new code must be adjusted until they do. 5. Refactor code. The growing code base must be cleaned up regularly during test-driven development. New code can be moved from where it was convenient for passing a test to where it more logically belongs. Duplication must be removed. Object, class, module, variable and method names should clearly represent their current purpose and use, as extra functionality is added. As features are added, method bodies can get longer and other objects larger. They benefit from being split and their parts carefully named to improve readability and maintainability, which will be increasingly valuable later in the software lifecycle. Inheritance hierarchies may be rearranged to be more logical and helpful, and perhaps to benefit from recognized design patterns. There are specific and general guidelines for refactoring and for creating clean code. By continually rerunning the test cases throughout each refactoring phase, the developer can be confident that process is not altering any existing functionality. The concept of removing duplication is an important aspect of any software design. In this case, however, it also applies to the removal of any duplication between the test code and the production code, for example magic numbers or strings repeated in both. To make the test pass in step 3, repeat starting with another new test. The cycle is then repeated to push forward the functionality. The size of the steps should always be small, with as few as 1 to 10 edits between each test run. If new code does not rapidly satisfy a new test, or other tests fail unexpectedly, the programmer should undo or revert in preference to excessive debugging. Continuous integration helps by providing revertible checkpoints. When using external libraries, it is important not to make increments that are so small as to be effectively merely testing the library itself, unless there is some reason to believe that the library is buggy or is not sufficiently feature-complete to serve all the needs of the software under development. Development style. There are various aspects to using test-driven development, for example the principles of keep it simple, stupid, and you aren't gonna need it. By focusing on writing only the code necessary to pass tests, designs can often be cleaner and clearer than is achieved by other methods. In test-driven development, by example, Kent Beck also suggests the principle, fake it till you make it. To achieve some advanced design concepts such as a design pattern, tests are written that generate that design. The code may remain simpler than a target pattern, but still pass all required tests. This can be unsettling at first, but it allows the developer to focus only on what is important. Writing the tests first. The tests should be written before the functionality that is to be tested. This has been claimed to have many benefits. It helps ensure that the application is written for testability, as the developers must consider how to test the application from the outset rather than adding it later. It also ensures that tests for every feature get written. Additionally, writing the tests first leads to a deeper and earlier understanding of the product requirements, ensures the effectiveness of the test code, and maintains a continual focus on software quality. When writing feature-first code, there is a tendency by developers and organizations to push the developer onto the next feature, even neglecting testing entirely. The first TDD test might not even compile at first because the classes and methods it requires may not yet exist. Nevertheless, that first test functions as the beginning of an executable specification. Each test case fails initially. This ensures that the test really works and can catch an error. Once this is shown, the underlying functionality can be implemented. This has led to the test-driven development mantra, which is red, green, refactor, where red means fail and green means pass. Test-driven development constantly repeats the steps of adding test cases that fail, passing them, and refactoring. Receiving the expected test results at each stage reinforces the developer's mental model of the code, boosts confidence and increases productivity. Keep the unit small for TDD. A unit is most commonly defined as a class, or a group of related functions often called a module. Keeping units relatively small is claimed to provide critical benefits, including reduced debugging effort when test failures are detected. Having smaller units aids in tracking down errors. Self-documenting tests. Small test cases are easier to read and to understand. Advanced practices of test-driven development can lead to acceptance test-driven development and specification, by example, where the criteria specified by the customer are automated into acceptance tests, which then drive the traditional unit test-driven development process. This process ensures the customer has an automated mechanism to decide whether the software meets their requirements. With ATDD, the development team now has a specific target to satisfy the acceptance tests, which keeps them continuously focused on what the customer really wants from each user story. Best practices. Test structure. Effective layout of a test case ensures all required actions are completed, improves the readability of the test case, and smooths the flow of execution. Consistent structure helps in building a self-documenting test case. A commonly applied structure for test cases has setup, execution, validation, and cleanup. Setup. Put the unit under test or the overall test system in the state needed to run the test. Execution. Trigger. Drive the UUT to perform the target behavior and capture all output, such as return values and output parameters. This step is usually very simple. Validation. Ensure the results of the test are correct. These results may include explicit outputs captured during execution or state changes in the UUT and UAT. Cleanup. Restore the UUT or the overall test system to the pre-test state. This restoration permits another test to execute immediately after this one. Individual best practices states that one should separate common setup and teardown logic into test support services utilized by the appropriate test cases. Keep each test oracle focused on only the results necessary to validate its test. Design time-related tests to allow tolerance for execution in non-real-time operating systems. The common practice of allowing a 5 to 10% margin for late execution reduces the potential number of false negatives in test execution. Treat your test code with the same respect as your production code. It also must work correctly for both positive and negative cases, last a long time, and be readable and maintainable. Get together with your team and review your tests and test practices to share effective techniques and catch bad habits. It may be helpful to review this section during your discussion. Practices to avoid, or anti-patterns. Having test cases depend on system state manipulated from previously executed test cases. Dependencies between test cases. A test suite where test cases are dependent upon each other is brittle and complex. Execution order should not be presumed. Basic refactoring of the initial test cases or structure of the UUT causes a spiral of increasingly pervasive impacts in associated tests. Interdependent tests. Interdependent tests can cause cascading false negatives. A failure in an early test case breaks a later test case even if no actual fault exists in the UUT, increasing defect analysis and debug efforts. Testing precise execution behavior, timing or performance. Building all-knowing oracles. An oracle that inspects more than necessary is more expensive and brittle over time. This very common error is dangerous because it causes a subtle but pervasive time sink across the complex project. Testing implementation details. Slow-running tests. Benefits. A 2005 study found that using TDD meant writing more tests and, in turn, programmers who wrote more tests tended to be more productive. Hypotheses relating to code quality and a more direct correlation between TDD and productivity were inconclusive. Programmers using pure TDD on new projects reported they only rarely felt the need to invoke a debugger, used in conjunction with a version control system, when tests fail unexpectedly. Reverting the code to the last version that passed all tests may often be more productive than debugging. Test-driven development offers more than just simple validation of correctness, but can also drive the design of a program. By focusing on the test cases first, one must imagine how the functionality is used by clients. So, the programmer is concerned with the interface before the implementation. This benefit is complementary to design by contract as it approaches code through test cases rather than through mathematical assertions or preconceptions. Test-driven development offers the ability to take small steps when required. It allows a programmer to focus on the task at hand as the first goal is to make the test pass. Exceptional cases and error handling are not considered initially, and tests to create these extraneous circumstances are implemented separately. Test-driven development ensures in this way that all written code is covered by at least one test. This gives the programming team, and subsequent users, a greater level of confidence in the code. While it is true that more code is required with TDD than without TDD because of the unit test code, the total code implementation time could be shorter based on a model by Muller and Padberg. Large numbers of tests help to limit the number of defects in the code. The early and frequent nature of the testing helps to catch defects early in the development cycle, preventing them from becoming endemic and expensive problems. Eliminating defects early in the process usually avoids lengthy and tedious debugging later in the project. TDD can lead to more modularized, flexible, and extensible code. This effect often comes about because the methodology requires that the developers think of the software in terms of small units that can be written and tested independently and integrated together later. This leads to smaller, more focused classes, looser coupling, and cleaner interfaces. The use of the mock object design pattern also contributes to the overall modularization of the code because this pattern requires that the code be written so that modules can be switched easily between mock versions for unit testing and real versions for deployment. Because no more code is written than necessary to pass a failing test case, automated tests tend to cover every code path. For example, for a TDD developer to add an else branch to an existing if statement, the developer would first have to write a failing test case that motivates the branch. As a result, the automated tests resulting from TDD tend to be very thorough. They detect any unexpected changes in the code's behavior. This detects problems that can arise where a change later in the development cycle unexpectedly alters other functionality. Madisky provided an empirical evidence regarding the superiority of the TDD practice over the classic test last approach, with respect to the lower coupling between objects. The mean effect size represents a medium effect on the basis of meta-analysis of the performed experiments, which is a substantial finding. It suggests a better modularization, easier reuse and testing of the developed software products due to the TDD programming practice. Madisky also measured the effect of the TDD practice on unit tests using branch coverage and mutation score indicator, which are indicators of the thoroughness and the fault detection effectiveness of unit tests, respectively. The effect size of TDD on branch coverage was medium in size and therefore is considered substantive effect. Limitations: test-driven development does not perform sufficient testing in situations where full functional tests are required to determine success or failure, due to extensive use of unit tests. Examples of these are user interfaces, programs that work with databases, and some that depend on specific network configurations. TDD encourages developers to put the minimum amount of code into such modules and to maximize the logic that is in testable library code, using fakes and mocks to represent the outside world. Management support is essential. Without the entire organization believing that test-driven development is going to improve the product, management may feel that time spent writing tests is wasted. Unit tests created in a test-driven development environment are typically created by the developer who is writing the code being tested. Therefore, the tests may share blind spots with the code. If, for example, a developer does not realize that certain input parameters must be checked, most likely neither the test nor the code will verify those parameters. Another example: if the developer misinterprets the requirements for the module he is developing, the code and the unit test he writes will both be wrong in the same way. Therefore, the test will pass, giving a false sense of correctness. A high number of passing unit tests may bring a false sense of security, resulting in few additional software testing activities, such as integration testing and compliance testing. Tests become part of the maintenance overhead of a project. Badly written tests, for example, ones that include hard-coded error strings or are themselves prone to failure, are expensive to maintain. This is especially the case with fragile tests. There is a risk that tests that regularly generate false failures will be ignored, so that when a real failure occurs, it may not be detected. It is possible to write tests for low and easy maintenance, for example by the reuse of error strings. And this should be a goal during the code refactoring phase described above. Writing and maintaining an excessive number of tests costs time. Also, more flexible modules might accept new requirements without the need for changing the tests. For those reasons, testing for only extreme conditions, or a small sample of data, can be easier to adjust than a set of highly detailed tests. However, developers could be warned about over-testing to avoid the excessive work, but it might require advanced skills in sampling or factor analysis. The level of coverage and testing detail achieved during repeated TDD cycles cannot easily be recreated at a later date. Therefore, these original, or early, tests become increasingly precious as time goes by. The tactic is to fix it early. Also, if a poor architecture, a poor design, or a poor testing strategy leads to a late change that makes dozens of existing tests fail, then it is important that they are individually fixed. Merely deleting, disabling or rashly altering them can lead to undetectable holes in the test coverage. Test-driven work. Test-driven development has been adopted outside of software development, in both products and service teams, as test-driven work. Similar to TDD, non-software teams develop quality control checks for each aspect of the work prior to commencing. These QC checks are then used to inform the design and validate the associated outcomes. The 6 steps of the TDD sequence are applied with minor semantic changes. Add a check replaces add a test. Run all checks replaces run all tests. Do the work replaces write some code. Run all checks replaces run tests. Clean up the work replaces refactor code. Repeat. TDD and ATDD. Test-driven development is related to, but different from acceptance test-driven development. TDD is primarily a developer's tool to help create well-written unit of code that correctly performs a set of operations. ATDD is a communication tool between the customer, developer, and tester to ensure that the requirements are well-defined. TDD requires test automation. ATDD does not, although automation helps with regression testing. Tests used in TDD can often be derived from ATDD tests, since the code units implement some portion of a requirement. ATDD tests should be readable by the customer. TDD tests do not need to be.